Hello, welcome back to Calculus. We're going to get started in Chapter 7. Chapter 7 is all about methods of finding antiderivatives. Finding antiderivatives, unlike derivatives, there aren't kind of systematic methods to do it for all possible functions. But in the first four sections of this chapter, we're going to learn a pretty wide set of tools that will allow us to find antiderivatives for many functions. And you know that finding antiderivatives is very important because, well, if nothing else, it's how we evaluate definite integrals, which we've seen some geometric applications of in Chapter 6. And in Chapter 8, we'll look at applications of the definite integral to all kinds of other disciplines. All right, so this first section is our first of what we will soon call our techniques of integration, and it's a technique of integration called integration by parts, or I just like to call it IBP for short. All right, so what are we going to have to do in this lecture? I want to derive the formula for it. I want to do a ton of examples. I hope it's not too ambitious, but I'm going to shoot for 7. If this video starts getting ridiculously long, maybe I'll cut it into 2 videos, but I'd like to illustrate the integration by parts method by doing lots of examples. You're going to try lots of them in your practice problems in the text. And then you'll see this won't make sense now because we haven't looked at the formula, but what we're going to try to talk about, like, well, when do we use it? And how do we choose U? What does that mean? Well, there's a U in the formula I'm going to show you. So there's some choice involved in this method, and the choices that you make won't always work out, but that's okay. If they don't work out, you can back up and make other choices. All right, let's get going. So let's start by deriving the formula for integration by parts. So I'm going to start by, I've got it all written out. I want to review from Math 109 the product rule for differentiation. Right? So the product rule, you remember, is more complicated than sums or constant multiples. If you're going to take the derivative of the product of 2 functions, f and g, I'm not writing f of x, g of x, and so on. I'm just being a little short here. F means f of x, g means g of x. So I'm taking the product of f and g and taking their derivative. How do you do it? Well, you don't differentiate f, multiply it by the derivative of g plus the other way around. Right? That's the way the product rule works. And what have I got in my second line here? Just integrate both sides. If you integrate the derivative of f times g, well, you just get f times g, right? Integrals and derivatives undo each other. On the right-hand side here, I just threw parentheses around what was there and integrated it. But it's a sum, and the integral of a sum is the sum of the integrals. So I split those things off. And then all I did in the next line is I algebraically solved for this thing. FG prime, it's kind of a random thing to do. If you're wondering why did he do that, well, I'll tell you in a second, but I'm just telling you what I did. I solved for that thing so I can see that the other 2 pieces, the F prime G and the FG, are both here. The minus sign is because I had to subtract this piece from both sides of the equation to solve for the thing I underlined in red. Okay, so you guys with me? We're doing good here. So what do we care about that? I'm going to make a little bit of a variable change. This is the formula that I'm after, actually, but I'm just going to kind of write it in a different way. I'm going to call f equal to u. If you want to see where I'm looking in the formula, I'm looking right there. That's that f. And then the rest of this stuff, it looks like the derivative of something. So this is a little bit weird, but I'm going to call it dv. Yeah, so those 2 things I'm kind of given. dv is this g prime times dx. So this side of my formula actually looks like the integral of u dv by those definitions. I just made it look like that. Okay, but now I'm going to do some computing. I'm going to write the things that I'm computing in sort of a different color. Which color do I like? I think I like this one. I'm going to compute du, just like I was doing a u substitution. So du would be f prime of x dx. Yeah, I don't know what f is, but it would be its derivative times dx. And if I've called dv g prime of x dx, well, then v would have to be g. Okay, and what's the color scheme about? I computed the values that I'm writing in that pink color. I was given the values that I wrote in black. All right, that'll be important as we do our examples. Keep that in mind. And then what's this formula say? Well, using those same variable substitutions, f times g just gets renamed uv. And then this guy, g times f prime of x dx, well, that's just v times du. Okay, so you're probably maybe head spinning. It's a lot of letters. What am I talking about? Why would I rewrite this thing? Why did that thing do that? Oh, never mind. I was trying to draw a nice box around it, but I'm not going to edit this video. Now you know I don't edit my videos, although you probably suspected it. This formula is called the integration by parts formula. All right. It's not quite a perfect formula. It doesn't, it's the question that we're going to be given is this thing once we recognize it, once we choose u and dv. It's those choices I was talking about. And it tells us the antiderivative we want to know, well, it's equal to something, which we could compute explicitly, minus, well, some other antiderivative. But you're hoping that when you make your choices, that this one's easier. Yeah, if that one's easier, it won't always be, but if it is, life is good because that's how we'll finish the problem. Okay, so pause the video for a second and jot this down where you can refer to it, the integration by parts formula. I'm going to be using it a lot. Before we start looking at some examples, I'll just tell you, somebody's going to hand me this, and I'm going to pick the u and the dv. Just has to be picked so that when I multiply them together, I get the whole integrand. And then I'm going to go compute du and v and write down this side of the formula and hope I can finish by doing that integral. Okay, let's try it out. Here's my first example. Oops, it's a little bit naked there, sorry. It's e to the x times x dx. I'd like to find an antiderivative for the function x times e to the x. Okay, how do I know to use integration by parts? Well, I never know. I never know to use integration by parts, but my suspicion is it might work because I'm looking at a product. We'll talk more about that later. So now I'm going to make some choices. At the beginning, when you start doing this, you're not going to know how to choose. I'm going to try to show you a lot of examples and you'll quickly develop a sense, but the rules are that when you're done, u times dv has to be everything that's here. Okay, so I'm going to pick u to be x, and then dv, I'm just going to let be the rest, which is e to the x dx. The dx will always go in the dv. It always goes in the differential. All right, but I had other choices. I could have picked u to be this, and dv to be that, and so on. I'll show you. Well, we can try some other choices. Okay, so I pick those, and now in this lecture, the colors are going to work like this. I derive this other stuff, right? If u is equal to x, du is dx. That's nice. Dx is simpler. One is a simpler function than x. To find v, I have to take an antiderivative. I have to ask myself, what function's derivative is e to the x? Well, e to the x. So you see, finding v in itself involves antidifferentiation. All right, and now, did you write it down? I'm going to use I'll just write its initials over the equal sign. I'm going to use the integration by parts formula. The integration by parts formula says I should take u times v, that's x times e to the x, and subtract the integral of v du. That's e to the x dx. Good. I'm not done because I have a second integral that I need to compute, but in this case, I think life is looking pretty good. This x e to the x goes along for the ride. The antiderivative of e to the x is e to the x. And now I'm not going to anti-differentiate anymore, so I add the ubiquitous constant, and there's my answer. What's a function whose derivative, or here's an infinite family of functions whose derivative, any member of which is x times e to the x. That's the general antiderivative. I'm not going to make this video long and check it, but you can stop the video and check. Maybe this is a good way for you to review the product rule. Maybe it's been a while. I need your calculus to be sharp as we proceed, but you can check that if you differentiate that expression using the product and difference rule, you're going to get x times e to the x. Do it. Do it. Okay, but I'm not going to do it because we're moving on here. We're 9 minutes into this. I've done one example. You know what I wanted to do real quick, just to show you, what if some other choices were made? What if some other choices were made? What if I let u equal e to the x and I let dv be x dx? It's not wrong. Du is e to the x dx. V would have to be 1/2 x squared. Okay, you can kind of see, though, it doesn't feel very good. du is not any simpler than u. V actually got more complicated than dv. That's not that good. The parts formula would say that this thing is equal to 1/2 x squared e to the x, that's my uv, minus the integral of v du. So that's 1/2 x squared e to the x dx. Okay, it's not false. This equality is perfectly true. It's just that the integral 1/2 x squared e to the x dx, that's more complicated than the original question. It's got the same form. It's a polynomial times an exponential, but the degree went up. Yeah, so I didn't do anything bad. I didn't do anything wrong. I'm still a good person. It's just that this choice of u and dv led to an integral that was a little bit more complicated than the first one. It's okay. It's okay. It just means I have to try something else. Try something else. You'll gain experience. But I'm taking the time to belabor this in the video that I didn't want to be long, because it's important for you to know that, like, the best way to learn how to choose u and dv well is to flub it a few times. Yeah, you mess up and you choose them unwell, because the very process of understanding, like, well, why didn't that work out? It's sort of the best way to learn how to do it. Okay, but you never know at the beginning. All right, now let's just try to crank through some of these. This one, yeah, I'm going to do it. I'm going to do it. So this is also a polynomial times an exponential. And I'm going to let u equal x squared and let dv equal e to the x dx again. And then switching my pen color, I can write that du is 2x dx and v is e to the x. Okay, so the parts formula says it's uv x squared times e to the x minus the integral of v du. So that's 2x e to the x dx. Notice I kind of took them out of order. I could write 2x dx e to the x or e to the x 2x, but this is sort of, but the important part with multiplication is that all the factors are there. 2x dx and e to the x. It doesn't matter what order I write them. This is just the way my eye is used to seeing them. Okay. I'm talking fast because this is getting long, but here I'll bring out that 2, and then look at that thing. This integral that we have to do before we're done, that itself needs parts. It can happen. It can happen. Maybe in like a little bonus video, I'll show you how to handle these things, but it's happening because this exponent was bigger than 1. You know, I mean, you could probably guess just from what we've done. If that exponent was a 3, we'd need parts 3 times, 4 times, and so on. So we just happen to work out the answer to what's in those red brackets. Do you remember it from above? So we don't have to reinvent the wheel since we just had it. The answer to that thing was that. Yeah, so I can just throw that on and we're done. So this is from example 1. So I'm not going to do the parts here again in the video. I mean, this video is, where are we at? We're at 13 minutes already, so I'm not going to do it again. But that, in general, don't be surprised if your parts has some parts in it. It can happen. All right, let's try another one. Here's a polynomial times a trig function. It's not an exponential function. I'll say something about this at the end, but you know, trying u equals the polynomial part is never a bad idea. I shouldn't say it's never a bad idea, but it's often a good idea. There, how's that? Let u equal x and dv equal sine x dx. So I should be emphasizing this, that together, those things account for everything. And now I'm computing, what's an antiderivative for sine? You gotta go slow there and say, well, it's opposite of cosine, right? The opposite of cosine's derivative is negative sine, or sine. Nice. So parts formula, u times v, that's minus x cosine x, minus the integral of v du, that's minus cosine x dx. And you can certainly write that as plus. Lots of chances to make sign errors in this business. Okay, that integral now, the integral of cosine, what's the antiderivative of cosine? It's sine. Check it. There's your second application of parts. Pause, think, reflect. I'm moving on. I'm going to just go fast here. This one doesn't look like parts. It doesn't look like parts. There's not times anything. I can't let u equal log x, or so sorry, I have to let u equal log x, because if I let dv be log x, well, what v is exactly what this question is. I don't really have a choice, but this doesn't feel quite like the other examples. So let me let u, and then what's dv? Well, what's left? It's just dx. Yeah. So switching pens here. What do we got here? du. Do you know it by heart? The derivative of the logarithm is the reciprocal function. What's the antiderivative of 1? Sometimes this hangs people up. Well, the constant 1 here, well, its antiderivative is x, right? That's the power rule. That's the power rule. Okay, so what's u times v? Well, it's x log x. I'm going to write it in that order. Minus the integral of, I'll write it, x times 1 over x dx, but that's nice. I love this. X times 1 over x is just 1, so that's an antiderivative I can do. The antiderivative of 1 is 1. We're done anti-differentiating. Nice. Okay, slow down, think about it. I'm moving on. Check this one out. This is just like the one we just did. Polynomial times trig. It's got a little noise in here. There's a 5, there's an 11. You can treat this 5 any way you want. I personally would just park it out front. I can't do that with the 11 because it's inside the cosine, but why not just park that 5 out front, and then for the rest of the problem, don't forget the 5, but just focus your attention on this part. Just some efficiency advice. Let's let u equal x. So dv is cosine of 11x. Okay, so du is just dx. That's a good sign. V, by a substitution, really, right? Cosine of 11x. For purposes of this video, I'm just going to write the antiderivative. It's 1 over 11 sine of 11x. But you might need to do, it's hard for me to call it a u substitution right now because the letter u is already being taken, but this might need a substitution, yeah? Maybe I'll make a little video on things like this, linear substitutions. You can get used to doing that to where you can, I'm not fancy, but I know a way to think about that I don't have to write out the details of all this, the substitution. Okay, so I've got my ingredients. Let's see what the parts formula does. Remember my 5, it's out there in front. So I'm looking at uv. So it looks like 1/11th x sine of 11x, and then I need to subtract the integral of v du. So that looks like 1/11th sine 11x dx. Yeah, did I get the pieces right and end that bracket? So that's 5. Nothing going on with this stuff, but it's going along for the ride. Got an 11th out front. Antiderivative for sine is negative cosine. So you got to watch carefully here. I'm going to do this negative, so it makes that a plus. Cosine 11x, well, times an 11th. So I should square that. Plus my constant. Oops, sorry about that. Okay, so what do we have? 5. Be patient, write it one more time. 1 over 121, 11 squared, cosine 11x plus a constant. Please check it with differentiation. It'll help you understand the method. All right, pause, soak it up. Here we go. Sixth one. Also doesn't look like parts. No choice. All we can do is differentiate that and anti-differentiate dx. Antiderivative is just x. Pause the video and look it up if you don't know it. You don't see this one all the time. I'd have to look it up after a while, but yeah, it's 1 over x squared plus 1. Arctan is a derivative, you know. Good. uv is x arctan x minus the integral of v du. Aha, look at that. That integral looks a little, oops, sorry about that. And I didn't put my dx. I'm going too fast for myself. So we have to do that integral. That integral involves a substitution. Yeah, I'll get you started. You need to let u, or I can't let u, u's already taken. Let w equal x squared plus 1. So dw is 2x dx. So this thing has the form 1/2 integral of 1 over w dw. Okay. So what's that? That's 1/2 the logarithm of w, and w is x squared plus 1. Now we integrated that thing. So there's the antiderivative of the arctangent function. Yeah, yes. So we're kind of expanding the number of functions we can take antiderivatives of pretty rapidly here. It's nice. Nice. Okay, pause. Take a break. I'm going to move on, but you can just come back. It's the beauty of videos. Let's check out this one, example 7. We're getting deep. This one, e cosine, their derivatives don't really get simpler. I'm going to just let u equal e to the x. Oops. To keep my faithful to my colors, let dv equal cosine x dx. Switching, now I can compute du. It's also e to the x. V is, well, the sine. The derivative of sine is cosine. Okay, so the parts formula says I get a uv, e to the x sine x, minus the integral of v du. That's e to the x sine x dx. Very similar to the given, but not quite the same. I don't have cosine anymore, I've got sine. Well, so let's try parts again. I'm going to forget about these definitions of u and v. I'm going to use the same letters again. I don't care about them here. I can even scroll them away to help you psychologically forget they were ever there. And I'm going to let u be e to the x again. dv this time is sine x dx. And I'm going to grab my pink pen and compute du. E to the x. V, the antiderivative of sine, is the opposite of cosine. I've got some stuff to carefully drag along here. And now I'm going to put a bracket because I'm replacing this integral with something with more than one term, and I don't want to blow that minus sign. So what have I got here? I've got negative e to the x cos x minus the integral of v du. That's minus a minus, this one and this one, if you're wanting to know. So that's plus e to the x cos x dx. So I feel like I'm getting kind of dizzy here. I got to be patient and write these terms. I'm distributing a minus sign. And I've got now minus that. And yeah, I'm kind of getting sick of this. Where are we? We're back where we started. Let me do a little iPad magic here and bring this down to help you remember. Whoa, not that much iPad magic. What's equal to this? Look at that. The exact integrand that we started with, e to the x cosine x, is here. It's just that there's an equation, and this side it's showing up with a minus sign. Maybe I can help and put the equation on one line, one more little bit of trickery here. So let me park that right there. Let me hide that yellow thing. It's distracting. And then let me take this thing and park it down here. I need to squeeze it a little bit. Get rid of the distraction. So you see what I'm going to do? I'm going to take this thing and add it to both sides of the equation, because it'll cancel over here, of course, because it's there with a minus sign. And over here, I'll have two of them because it's the exact same expression. So that thing means that 2 times the integral that I'm after is equal to, I'm going to factor this e to the x out so I don't have to write so much, sine x plus cosine x. Okay, and if I just divide both sides by 2, oops, I'm almost out of room here. If I divide both sides by 2, the question we asked, what's the antiderivative of e to the x times cosine x? Well, it's 1/2 e to the x quantity sine x plus cosine x. Well, plus a constant. Nice. That was fun. So that's kind of an elaborate, almost exotic parts problem. I call that thing a looper. Yeah, we had to kind of loop through the parts twice, and then we did something sneaky. We found an antiderivative, not by directly doing it, but we found an equation that contained it in a way that we could solve the equation for it. Yeah, it's kind of neat. Okay, so let's wrap up. We're about 26 minutes in. It's good. It's not unbearably long. How do you use some strategy to do this? How do you use some strategy to do parts? Well, there's no magic recipe, but when do you use it? When do you use parts? It works really well for functions that are polynomials. So what are polynomials? They're things with powers of x. Yeah, they can have more than one term and so on. Times, so there's a product with things like exponential functions, any of the trigonometric functions, logarithm functions. All right. So that's kind of a general recipe of when to think to use to parts. You won't always know. It also works really nicely on inverse functions. We did inverse tan. You can try inverse cosine. The logarithm, we did that one too. The logarithm is the inverse of the exponential, right? So those are sort of some general guidelines of functions that it works well for. And then, well, what about this choosing the u? There's no recipe. I'd be famous if I knew a magic way to always choose it correctly. So this is just some advice, but some people like this acronym, LIATE. I don't know if it's easier to know it or whatever, but it's some general advice that this is the order to try to choose u. So try to choose u equal to logarithm. So a logarithmic function is involved, differentiate it and see if you can anti-differentiate other piece. Inverse functions. So inverse tan, inverse cosine, if that's in there, try to let u equal that. And it's in this order. So try in this order. Not a fail-safe advice, but algebraic functions is what the A stands for. So things like polynomials, radicals, yeah, rational functions, polynomials over polynomials, algebraic functions, those are called. Sorry, I'm trying to do this, but I'm running out of room. Trig functions, and then finally exponential. So worst case scenario, that's some general advice of how to choose u. Okay, notice that in my looper, I actually violated this. I let u equal the exponential and dv be the trig. It could have gone the other way. Okay, I hope that was helpful. We're going to look at integration by parts with definite integrals next time, but I'm going to stop this now. Thanks for listening.